welcome from me on behalf of Milhouse Electronic to all of you here for our first Tabor webinar with the title Multiple Channel Phase-Coherent RF Signal Generation for Massive MIMO Advanced Radar and Quantum Computing with the specialist John Marcade from Tabor Electronics. Tabor Electronics has been founded in Nesha, Israel in the year 1971. It specializes in high-end test and measurement domain like multi-channel RF generators, arbitrary waveform generators, and transceivers, which are used for the applications in aerospace, quantum physics, radar, etc. Also, it has experience in OEM domain like developing solutions for well-known companies like Keysight, LeCroy, Keithley, etc. Over the years, Tabor has gained a high level of expertise, technological progress, and best possible quality at affordable prices. So, and to John Marcade, he is a field application engineer for Tabor and responsible for quantum physics for Proteus products like arbitrary waveform generators and transceivers. And today, he's our presenter. So, one other two. Sorry. Then I briefly introduce my company, Milhouse Electronics. Founded in 1977 near Munich, Milhouse Electronic offers know-how, innovative developments, and individual customer-specific EMC-compliant solutions for professional measurement and technologies and data communications. Areas of applications are in laboratories, industry process, automation, RF measurement technology, etc., up to research and development as well as university and training. Our product range includes measuring instruments, data loggers, interfaces, cable testers, software, as well as PC cards and components for Ethernet LAN, also generators, etc. You can find us at www.milos.com. So one more small note. Please all leave your microphones on silent, please. And you can write your questions by email to sales@milos.com. Then we will come briefly to the topic overviews. At the beginning, we will start with the different applications areas like MIMO, advanced radar, and quantum computing. After that, we hear about the RF design engineering of complex RF systems, such as those implemented in quantum interfacing, advanced radar, EW, 5G, and other wireless communication technologies, and automotive. Then John demonstrate possible solutions with the new Lucid multi-channel analog RF signal generators. And finally, they review the basic system architecture and technical features in accordance with the relevant applications. So then I will turn now over to John now. One moment.
First of all, I want to thank you all for attending this webinar. It's going to be short, so I will try to be as fast as possible in order to cover all the topics. My name is Joan Mercade. As has been said, I am the application engineer for one of the application engineers for Tabor, and I will go through this presentation today on multi-channel RF signal generation. And I will focus first in the different application areas where basically I will talk about the requirements that are expected from instruments applied to these areas, and then I will go through some of the solutions, and finally I will cover a little bit the Tabor solution for this application environment, which is the Lucid multi-channel series of generators that we will see at the end of the presentation. After that, we will have some questions and answers, and then this will be the end of the presentation. Okay, let's go for it. First of all, I'm going to talk about the application areas that I'm going to cover today. There are more than that, but I will cover those because I think those are the most important ones in terms of size and complexity. And as you see, I will cover phase array radar and beamforming, basically applications for either and beamforming are applications where you need to have multiple antennas working together to steer one of the beams or multiple beams. Then I will cover MIMO or massive MIMO for wireless communications, which is an area where you need multiple antennas, but in this case, transmitting different contents to increase the bandwidth of the capacity of the channel. Then I will go through quantum computing and research, which is a very specific area where multiple modulated RF signals are required. Then I will talk a little bit about local oscillator substitution and general purpose analog signal generation. And finally, multitone test, which is a very specific test methodology to test both the linear and nonlinear behavior of systems or RF systems and the components. Okay, let's go for the first application area, which is going to be phasor radar and beamforming. In modern radar systems, multiple antennas are used in many times, in many applications, to steer one or multiple beams. So instead of moving an antenna mechanically, nowadays it's possible to steer the beam by controlling the phase in multiple antennas, in what is called a phase array. Even more, in addition to steer the beam of the antenna, you can handle, because of this capability of controlling the phase over multiple signals, you can even handle at the same time multiple beams. For instance, tracking different targets at the same time. So this is a very important application for multiple antenna systems. In this case, in most cases, the basic same radar antenna, the same radar signal is applied to all the antennas, but those signals has to be transmitted with a very specific carrier phase, and ideally they should be transmitted with a specific delay. So basically, all the signals coming from the different antennas properly act together in a given direction or directions. So that's very important, and this is one very critical characteristic of a phasor array radar system, to be very accurate in the phase setting for all the antennas, and also for the delays between the different signals being transmitted. Okay, the same thing applies not only to transmission, but also for reception. So you can apply exactly the same technique to receive energy from one or different directions by controlling the relative phase with the reception antennas that are basically the same antennas that are used in different moments as transmitter and receivers. In this graphic here, you can see such an arrangement where you have 4 antennas. So you can transmit at the same time in different directions, and then the echoes are sent through a duplexer to the receiver side. Okay, so this is what it's being used in radar. The same thing applies to beamforming. In some modern wireless communication systems, the energy of some signal can be transmitted specifically in the direction to one of the users of the wireless network. So every receiver is getting a specific beam, so the power is maximized, the signal-to-noise ratio is maximized as well, and then you can even reuse the same frequencies in different directions with different subscribers. But basically, the way you handle the beams, the way you handle the antennas is very similar with phasor radar and beamform, because it is the basic principle, is the same basic principle that is being applied. Okay, when you try to test the transmitter side or the receiver side of a phasor array system, you need to have a proper signal generator to either feed the antennas with the proper signal, or to simulate the echoes being received, so you can apply these signals to the receiver, so you can test if the receiver works as expected, especially all the algorithms applied to target separation and identification. Okay, in this case, the traditional instrumentation or traditional generators being used for this application are VSGs, vector signal generators. or AWGs, arbitrary wafer generators that generate signals in the AF level or baseband, and then you'll use an external modulator or mixer to reach the right frequency. So those are the typical tools. The VSG, because modern radar systems use complex modulations as linear FM or phase modulation, and or AWGs that can create basically any signal that you may think about. Okay, when you have these kind of signals, these kind of generators, then you have to apply them to the phase array. And then the way to do it is by using multiple generators in some cases. And in some other cases, what you do is using one signal or a few generators and then using multiple mixers. So you can control the final frequency and the phase for the carrier by using some local oscillators that are used in addition to the AWGs in this case. Okay, when you use this approach, you have some limitations. One of them is the difficulty to reach very high number of channels. Keep in mind that having 2 or 4 channels may be something feasible, but when you try to generate tens or even hundreds of channels at the same time using traditional VSGs is not possible, not only because the size or the difficulty to lock them together to work at the same phase reference, but also because of the cost per channel and the size of the system. So this is not really an option. Well, this is quite difficult to configure. You use multiple devices, multiple local oscillators, multiple mixers or modulators or VSGs, a set of tens of instruments. This is very difficult to configure. This is very difficult to control, and this is also very difficult to lock to a reference signal with the right accuracy that you require for this kind of applications, where every tenth of a degree in the phase of the carrier is an important asset. Another important issue is that when you use these kind of approaches, it's almost impossible to generate more than one beam, because in order to generate more than one beam, you need to handle different phases for the antennas at different moments in time. And if you are controlling the phase of the different antennas using the phase of different local oscillators, or controlling the delay between the local oscillator and the mixer, you cannot do that on the fly. So basically, you can set up this for one direction, and then after all the tests are finished, you go to the next direction. So this means that you cannot generate multiple beams at the same time easily. The cost per channel, I already mentioned, and the scalability. So every time you need to increase the number of channels, it requires more and more equipment, more and more real estate in your lab, and it's something difficult to handle. Okay, so this is the situation in carrier phase control. You have one single source for your signal. Typically, it could be an AWG or a VSG with an IF signal, and then using an analog RF signal generator or multiple of them. In this case, I am showing the Lucid Series with 4 outputs, 4 independent outputs, so they are generating the same frequency, but we're controlling the phase for each one independently. So as you see, we can transfer the local oscillator to the different mixers. Then we can control the specific phase for each one of the antennas. So in this case, we can generate any beam that we are interested in, and that's the way it goes. In this case, as you see, the IF signal is using a power splitter. It's just sent to all the mixers. It's the same signal is reused. Of course, this is something that is feasible and it has been used, and is being used all the time, but it has some important drawbacks. And then this is basically the most important one. Here, what I did was using one of our instruments. I generate an arbitrary wafer generator. I generate pulse, a very short pulse, with a given phase with one of the channels, and then the same pulse with a different phase with another channel. So basically, it's the same pulse with 2 different carrier phases. And then what I've done is showing in the scope with the red delay. So I am simulating how you see these two signals from the direction you are steering the beam. So from the direction that you are steering the beam, all the faces for all the antennas look the same, as you can see here. The phase is superimposed. The problem is that because it is the same signal modulating the carrier, if we have the same phase, it's okay, but look at this. We have a delay between the pulse that is modulating the signal in antenna number 1 and the pulse that is modulating the signal in antenna number 2. When you add together, and this is what actually sees the target, when you are adding together the antenna contribution, you see that we have a perfect aligned phase for the carrier, but now, because we are at this delay, the shape of the pulse is not as steep as it was before. Okay, so we are distorting the pulse because of the differential delay between the antennas. We're using the same envelope, but with some delay. So at the end, we are distorting the signal. Now think in a more complex radar signal where you're using linear FM. This means that the signal, the instantaneous frequency here for one of the beams, for one of the antennas, excuse me, is not the same as the frequency here for the other antennas. So at the end, you are mixing together two different frequencies. This is not what you expect. You have to have the same frequency. If you're using polyphase, which is phase modulation, so the phase change in different moments in time within the pulse, the same thing happens. You are now interfering one chip with the next, so you are destroying the integrity of the signal. So just distributing the same waveform, or the same signal, IF signal, and then mixing it up does not guarantee a proper work of the system. That's something that for narrow band signals can be acceptable because everything is slow, but for wideband signals, and this is the case of radar and many other wideband signals today, like 5G, for instance, all these signals are very sensitive to these differential delays because as there are so much frequency range, in some frequencies you may have much higher interference than in others, especially when you go up in frequency. So that's something to think about. Of course, with this arrangement, you cannot have more than one beam. And of course, as the interpulse modulation is distorted as well as the power envelope of the signal. So this is not, this architecture here is not really a perfect solution. In some applications, you can reduce the differential delay by using multiple outputs, and then for each output you have a different delay, and then you are distributing each of the outputs to a series of antennas. So because you are distributing different phases, you can reduce a little bit the effects of the differential delay, but this is always a problem. So this is what you can see here. When you have this arrangement, you expect to have this perfect looking pulse, but because of all these distortions, you may end in a signal which is not flat. And if you look, for instance, this is a chirp, it's an linear FM signal. If you look at the profile for frequency versus time, you will see that it would incorporate some distortion. So that's very important for some applications because this destroys part of the resolution of the system. Okay, ideally, we can do a different thing, which is instead of just controlling the phase of the carrier, we can also control the delay between the IF signals. In this case, we are distributing different IF signals to the different mixers, and we are distributing as well different local oscillators with different phases. In particular, we could distribute exactly the same local oscillator to all the mixers and then control the phase for each antenna by using the IF signal itself. The IF signal itself could carry the information about the phase. So you can control delay and you can control phase. Okay, so in this case, you can avoid the problems that we have been describing before, because you have this capability of controlling both the phase and the delay of the signals applied to every antenna. Well, the nice thing about this is that this can be done with instruments that are available in the market. For instance, in Tabor, we have the Proteus, multiple channel AWG, where you can have tens of independent channels capable of generating signals up to 8.5 gigahertz directly. So you don't need to reduce the frequency at all. So if you want to use that to generate AF, you can do that in up to tens of channels. And then in one step further, you can go to this different arrangement. If your signal is, your transmitted carrier frequency is less than 8.5 gigahertz, you can directly create the RF signal, the microwave signal, without any external mixer or modulator. So you can just connect the outputs directly to the transmitter. So this is a different approach that we are trying to cover with the Proteus. Those instruments are also performing all the real-time digital modulation, IQ modulation, by using internal numerical converters. And then this means that you can have at the same time frequency agility, or you can redefine frequencies very quickly because you don't have to download a new waveform and so on. So this approach has many advantages like simplicity, because you don't need external modulators or mixers. The accuracy, there are no modulator alignments. You need to use an external IQ modulator. You will find all kind of quadrature errors or quadrature imbalance or differential delay, IQ delay. This is not happening when you use an internal numerical digital converter with IQ modulation. Everything is perfect. The modulation bandwidth is huge because you only depends on the sampling rate. With the Proteus family, we support up to 4 gigahertz of modulation bandwidth. So we can even support the widest bandwidth automotive radar that are being deployed with this instrument. The flexibility, the phase and pole is a very compact system. There are no microwave components that you have to take care, and the cost per channel is much lower, and you can even do real-time corrections for flatness or frequency response of external devices if you want. So basically, this is an ideal situation when your frequency is lower than 8.5 gigahertz. But if the frequency is larger than that, you still have this architecture here where you can use external mixers so you can reach any frequency that you may think. Okay, this is a Proteus modular device. In this 19 inches chassis, the PXI chassis, we have up to 40 channels in one single chassis that can transmit these signals. Those you see here are actual signals, radar signals. In this case, it's a linear FM signal, 5 megahertz bandwidth, that is being generated by using the direct conversion at 3.2 gigahertz. And this here shows you the RF quality. In this case, I'm showing you the ACPR for a signal. This is 20 megahertz bandwidth. And you can see we're in the range of 70 dBs at 1 gigahertz. So we're talking about quite good RF performance by using direct RF generation with digital tonal converters in AWGs. Okay, so that's the introduction for phase array and beamforming. Now we're going to talk a little bit about MIMO. MIMO, you know, stands for multiple input, multiple output. MIMO is a trick that has been used in many different wireless standards and applications, where you can increase dramatically the capacity of a wireless channel by using multiple antennas in the transmission and the reception. So basically, you transmit from one antenna to all the others, and then by using linear algebra, linear combinations of the inputs and outputs, and channel estimation, you can recover in the receiver each one of the transmitted signals in all the 4 antennas. So it's like having 4 times the capacity in this particular example, the capacity that you could have in one single antenna. So this is becoming more and more popular because it's a very good way to increase the capacity of course, bandwidth available for subscribers and or the number of subscribers. So this is being deployed on LTE, in Wi-Fi, in 5G, and even in radar. There start to be some radar technologies that are based in MIMO architectures. Many times, especially for mobile telephony applications and Wi-Fi applications, the MIMO architecture is combined with beamforming and frequency reuse as well. And now there is we're witnessing a very fast increase in the number of transmission and reception antennas. So we have come from MIMO to what is called today massive MIMO, where we're not talking about 4x4 or 2x2. We're talking about hundreds of different, tens of hundreds of different antennas and signals. Well, there are many commonalities between this application and the phase array radar and the beamforming application we have seen before, but there is a very important difference here. In this case, the signal being transmitted in each one of the antennas is different. If you want to emulate the transmitter, you need to apply different modulations to the different antennas. And then in the receiver, you want to generate some signals to emulate the path, the signal path. Then you have to apply all these linear transformation between the input and the output, so you can fit to each input in the receiver the right combination of the transmitted antennas with all the delays and all the phase and amplitude responses that are modeled for the channel. So many commonalities, but in this case, the main idea is that every signal here is not a delayed version of the other, it's a complete different signal. In fact, in some applications, even the carrier frequency is not critical. At the end of the day, the carrier, I mean the carrier, the phase of the carrier signal is not critical because at the end, you have to recover the signals no matter the carrier phase that you're receiving here. And carrier phase will depend on the path the signal has been following in the transmission. Okay, what are the traditional test solutions? Well, basically, if you look at the market today, there are some vector signal generators that are being promoted in the MIMO arena, and those devices are typically having or incorporating more than one channel that they can generate, typically 2, in some cases up to 4 channels with one single instrument, and this is what they support, up to 4x4. In some cases, you can also use, as we did in radar, you can use multiple AWGs, and again, you can use external mixers or modulators to create a MIMO system, a fully functional MIMO system as well. And then finally, you can also find devices that are instruments that are designed to test both transmitter and receivers, and those are those radio test sets that typically are also limited to 4x4 in most cases. Okay. Well, for massive MIMO, as I told before, we are not talking about 4x4 or 2x2. We are talking about 10x10 or even 100x100. So it's a complete different situation where traditional instrumentation is not really useful to generate a realistic system where you can emulate this kind of architecture. Okay, so if we go to quantum computing is a very different topic because it's not related with wireless or radio transmission, but it also uses all sorts of RF and microwave signals, multiple of them in a single qubit. And in operating quantum computers, you may have several or even several tens of qubits. So we are talking about situations where you need to control multiple qubits using multiple RF signals for each one of the qubits. So at the end, we end up with the requirements to generate anything from 3 to 4 from one single qubit up to 50 to 100 RF signals simultaneously with perfect timing and coherence for a complete quantum computing device. So we're talking about a very demanding application regarding RF signal generation. One of the reasons it's so demanding is because RF signals are not very complex. In fact, they are typically pulses. Those pulses are used to control the quantum state. So you're sending some pulses with some specific shape and frequency and phase. You can control how a qubit can go from one quantum state to a different quantum state following the quantum algorithm that you are executing in your computer, okay? So basically, this is the principle of controlling the qubits. Sending those RF pulses allows you to control the quantum state. The problem with that is that all these quantum systems are very sensitive to noise. So this is, in fact, many of those cannot operate, all of them today, cannot operate but at a very low temperatures, close to the absolute zero, in order to keep noise very low in the system, so you can keep the quantum state and also the coherence between different components in the quantum system. Okay, so any noise that you add to the system will result in the loss of the coherent state of the system. So this means that anything that is not perfect, you can also take consider it as being noise added to the system. So use an RF pulse to control the new quantum state, at least not with exactly the shape and duration and phase that are expected. It's just like adding noise to the system. So the most likely is going to fail. The computation is going to fail. So that's very critical. So we're talking about very accurate signal generation over tens, even hundreds of channels simultaneously. Very demanding application. In addition to that, you need to control this in a very quick fashion. So basically, you need to send pulse to position the quantum state of the qubits, and then you let them interact between them. So they produce the next quantum computation step, and then after the end of the process, you have to read the quantum state, process it, and then when it is processed, then you can decide what is going to be the next quantum state for each one of the qubits. So this is a closed-loop control system. The problem here is that in order to be useful, you have to do all the quantum computation steps in less than the time that you can keep the coherence of the system. And the quantum coherence of those systems can last for anything from microseconds to a few milliseconds in most cases. So you have to be very fast doing it. So that means that it's very demanding situation where you need to both generate signals, to capture those signals, process them very quickly, and then repeat the cycle. Okay, so at the end of the day, you have what you can see here. You have your quantum layer where the quantum computations are performed, and then you have a classical to quantum interface. Here, you control the quantum layer, and you also communicate with the classical computing system, which is both controlling the quantum computer, and at the same time, this system is used to validate the results that you obtain with the quantum computer. And what you see here is what we can call graphical to quantum interface. Is responsible for controlling the quantum state, reading the quantum state, and then doing the real-time closed loop control of the system. Okay, so you look at what is being used today. Basically, this is the way you control quantum states is by using multiple channel AWGs, where you can generate the pulses with the right timing and so on. And typically, you need to add something to reach the frequencies, the microwave frequencies that are required here. So typically, you add a bunch of IQ modulators or external mixers to reach the right frequencies. The other way around, you can also use those channels to send pulses to read out the quantum state. So you can know what is the end state after this quantum computation state. And this means that, again, you have to read this data at microwave frequencies. In order to do that, you use multiple channel digitizers. And again, because of the frequencies involved, you need to add external mixers and down converters to be able to capture this with a multi-channel digitizer. And then you have to do this. You have to do the closed loop control internally in real time using some real-time digital signal processing system. Okay, because you cannot afford, you don't have time to send information to the classical computing system and then getting the right outputs from the classical computing system. Okay, so that's the basic principle. Okay, so this is an example of such a system, and that is the traditional approach. In this traditional approach that has been very popular for many years in the area of quantum basic research for years. Quantum research has been specifically based in the validation of quantum technology. So basically the quantum qubit technologies, there are many of them available today, and there is still research, and also the way to control those qubits and the feasibility of performing quantum computation. Nowadays, we are transitioning to actual quantum computers, operating quantum computers. But the approach, the traditional approach has been the one you see here. Multiple channel AWG, generating control signal. In this case, we are generating an IQ signal, baseband signal, and then using an external IQ modulator, we are reaching the right frequency that is important for this qubit, and then we are controlling the qubit. And then in order to read out the state, we are generating with a different channel using another mixer. We are using the readout pulse, and then we are reading the pulse by down converting the signal to a lower frequency, and then using a digitizer, we capture the signal so we can close the loop somehow by using some processor or just using some trigger signal or whatever. What is important here is that this is just one single qubit. In this particular case, we're using 3 channels of an AWG, and we need to use 3 different local oscillators in order to feed the different mixers and modulators necessary for this single qubit. Just multiply this by 10, 15, or 20, or 40 qubits. This means a lot of channels in a single system. This is why you see that many cables between this between those racks and the quantum layer. The quantum layer is here in the refrigeration system, and those cables here are basically the signals that you see here for each one of the qubits. So very complex, very large system. Okay, in fact, the pulses, as I told you before, they are not very difficult, but you need to be very accurate, and you have to control both the magnitude and the phase. So this means that somehow you need INQ modulation, because you need to control both the magnitude and phase, and you have to be very accurate. Okay, Typically, those pulses are in anything between 3 gigahertz carriers and a few tenths of gigahertz, but the vast majority is below 7.5 or 8 gigahertz. So this is something that is quite common among all the qubit technologies. The shape of the pulses are very close to Gaussian shapes with a small variation, but you need to control both magnitude and phase. Okay, in this quantum computing application area, as you see, you may need multiple channels, AWGs, and you may need several local oscillators that you have to control individually in terms of frequency and also phase. So you need a bunch of multi-channel generators in this kind of application. You need AWGs with multiple channels, and you need multiple local oscillators to fit all the mixers and modulators. But keep in mind that the same approach that we have been presenting in the radar, phase array radar part of the presentation can be used here. Instead of generating the signals in the way we have shown in this slide, we could go with Proteus AWG and generate directly the modulated pulses, correct them in real time, so accuracy is perfect, and then you can generate tens of them by using a single device. So, and then you can get rid of the external modulators and mixers. So you have a much more compact, much more dense, and the cost per channel is much lower, and it's much easier to align and to correct because you don't need to correct external components. So that's our number one offering today for quantum computing is the Proteus line of multi-channel products, and then we also supply the Lucid multi-channel RF systems to provide for these multiple local oscillators in a very compact and cost-effective way. But one step further, the Proteus AWG is also a transceiver architecture device, so we can also incorporate in the same modules the digitizers that can work up to 9 gigahertz. So using both the transmitter and the receiver and internal real-time FPGA close in the loop, we can implement complete quantum computing control systems using a single set of devices. So much simpler, much more cost-effective. Well, we have seen now one of the examples where analog RF signal generator use of local oscillators. But this is a general need in any RF or microwave system where you have multiple frequency conversion stages, or where each one of the stages you're required to have local oscillator. So and multi-channel analog signal generator can be used to generate each one of these local oscillators being used in the system. But not only local oscillators, you can also use that to generate reference signals and also to generate clock signals as well. For instance, for D2A or A to D testing. That's important because the main problem is that typically instruments available in the market are limited to one channel, and then means that you need more than one frequency or different, or to control the phase of different local oscillators in different locations in your design. You need to keep adding additional signal generators. Using multi-channel RF signal generators simplifies a lot the requirements and the cost of channel. Finally, the last application we're going to see is the multitone. Multitone is a type of test that is quite popular in some situations because it gives you a very quick view of the linear and nonlinear behavior of some device. Basically, what you do is generating multiple equally spaced tones, and those tones are applied to the device under test. And then you look for the linear information. For instance, what is you apply a flat response number of tones where the amplitude is exactly the same. And then you look the tones at the output. Then you can establish what is the frequency response of the device under test. You can also look for the nonlinear behavior. In this case, for instance, we can see here intermodulation products that is being caused by the device that you're testing, for instance, an amplifier. You can take a look what's happening out of the channel, or you can even create notches so you can remove some of these tones and then look for the intermodulation products within the channel. This is what called the noise power ratio testing, where you look for this ratio between the amplitude of the tones and the amplitude of the intermodulation products within the channel. And this is what we call the noise power ratio. And of course, you can then take action to improve this, the performance of the system by improving this noise power ratio measurement. But this is not the only application. You can also use this kind of signal to look for image rejection in modular, or for look for or measure or establish which is the quadrature modulator alignment in an IQ modulator, or you can use this kind of signals as well to characterize D2A and A to D converters as well. Well, the traditional way to generate these signals is by using multiple continuum wave generators. So each one of the generators will be generating one tone, and then you combine them together by using a combiner. And then this is going to be your multitone signal. Of course, each one of the tones that you add together using a linear combiner is a very pure, if you are using a good enough analog continuum wave RF generator, you are going to have very large Fourier dynamic range. However, the number of tones depends on the number of generators you are using. So if you have 2 generators, you can generate 2 tones. You have 4 generators, you can generate 4 tones. So you are going to have a limited number of tones. Another important issue when you are testing for nonlinearity is to know what is going to be the peak to average power ratio. At the phase of these tones, it's independent. Sometimes they are going to add together and you are going to have high peaks. So it's very difficult to control the peak to average power ratio. And in order to get useful data, you have to use multitone signals which peak to average power ratio close to the kind of signals that the device is going to handle. For instance, you are going to generate LTE signals. Probably you will be looking for a multitone signal with less than 10 dB peak to average power ratio. You go beyond that, you are going to stress your amplifier or your modulator much more than it could be by the final application. So you are not going to get realistic results. So that's a very important issue. And of course, once you have added in some external component, let's say that you need to add an amplifier to have the right amplitude for the signal. Of course, when you add some external component, no matter how pure those tones are, any external component, active external component, will add intermodulation products. And this is quite difficult to compensate. However, this means that, for instance, in the new Lucid multi-channel signal generator, we have some models with 4 up to 16 channels in a single device. So this means that with the Lucid Series generators, you can very easily generate very high quality multitone signals with up to 16 tones. You use one single device, or a multiple of that, you use multiple Lucid instruments. Well, there's an alternative to that, which is using an AWG. In fact, you see here signals generated with the AWG with the Proteus unit. And as you see, this is the signal with some notch. This is the notch. And if you pay attention to the scales, you will see that we have more than 80 dB dynamic range in this measurement, which is a wonderful, amazing dynamic range for this measurement. And this is the same signal, but applied to measure the ICPR. In this case, we're getting more than to 72 dBs of ICPR. So we're getting a very good dynamic range, and this is not an RF device. This is a AWG. What is the trick? One of the tricks we have is that because AWGs can generate any signal that you can define mathematically, this means that you can define your multitone signals by defining the amplitude and the phase, which is one of the components. So as you can control very well the phase, you can properly control the peak to average power ratio. So this is one of the advantages of using an AWG. And of course, the D2A converters and all the output stages of an AWG are not as good from the linearity standpoint as a very high-end RF generator as the Lucid is. But because we are talking about an AWG, we can run some calibration procedures so we can get rid of all the intermodulation products generated by the instrument itself. And this is what we do. We're using our Multitone's algorithm, so we can get rid of both the in-channel IMD component and the adjacent channel IMD component. So we can get a very clean signal out of the AWG and frequencies up to 8 gigahertz. So that's a very useful test solution for this kind of applications. Okay. Well, finally, and this is the end of the presentation, a very quick look at the Lucid series of analog RF signal generators. In fact, this is a family of products. This is the benchtop product. As you see, it's a self-contained instrument with 1, 2, or 4 channels in it. But this is just one of the members of the family, because we have desktop single-channel device, a very small device. We have also portable single-channel devices, battery-operated, for testing in the field. And also we have multiple channel instruments, like the benchtop we have just shown in the previous slide, and also a rack mount unit with one version with up to 4 channels, and then another version with up to 16 channels in a single device. If we take a look to the general characteristics, as I said, we can have up to 16 coherent and synchronized channels in a single device. Coherent means that you can control both the amplitude, the carrier frequency, and also the phase for each one independently. But all of them are locked together, so you define the phase of one channel and the other. This phase is kept over time, so you can use that to control the phase in different components. And we reach today up to 12 gigahertz, but we have plans to introduce new products in the near future with 20 and even 30 gigahertz in the 20 and 30 gigahertz area. This is an analog signal generator, and of course we generate also analog modulations in addition to the continuous wave signals. We will talk about this now, but we are also planning to introduce in the near future vector signal generators as well. So we will combine in the same bots the INQ modulation, continuous wave generation, and arbitrary wave generation in a single package with a very high performance characteristics. Very low phase noise, wide range of output power from -90 to +15 dBm, very fast frequency switching, and we can both support internal and external modulations with AM, PM, FM, pulse, and also pattern. And we also support sweep modulations and list modulations. In the fact we can define a list of signals, list of frequencies where you can sequence the signal generation, so you can implement basically any custom or arbitrary sweep that you need for your testing. This is fully controllable using USB or depending on the instrument, Ethernet, and it's fully programmable, so you can automate your testing by using SCAPI commands and IBI drivers, and using any interface like I told before, SPI or USB or Ethernet. But we also do something which is very important for some users, because sometimes they look for some replacement for the old equipment they have, or just a more cheaper alternative. And then we can, but the problem is when you replace one instrument by another, especially if you are integrating those instruments in ATE systems, is that you have to rewrite the software to control the new instrument. But in this case, it's not necessary, because we also supply the instruments with emulation for commands from different vendors. So it's just taking one instrument from the rack and replacing it by the new one, and everything works from the very beginning. We have very good phase noise characteristics. This is the benchtop platform. It's single, dual, or four-phase coherent channels in one single package. Self-sufficient. So you have a 5" touch screen with a very friendly graphic user interface that you can use with any of the instruments. The same graphic user interface can be used with a rack mount instrument from a remote computer or with the desktop instrument. So you can do exactly the same thing with all of them using the same software environment. And it's very space efficient. Just take a look to this front panel, and then this is the rear panel. So you have all the modulation inputs. As I told you, we can modulate both internally and externally and independently. So this is why for this 4-channel instrument you have 4 different modulation inputs, because you may have different modulations for each one of the channels. One can be modulated FM, the other one AM, and so on. And the same thing happens for the trigger signal. They're independent for each channel, although they can work together as a single device if you want. We also have this removable SD card, so you can take all the frequencies and all the settings out if necessary. The same thing for the rack mount platform. As I told you, we have this 1U instrument with 1, 2, or 4 channels, and then we have a 3U instrument, so it's 3 times the height, but with 4 times the channels. So we can reach up to 15 channels in one single device. Fully synchronized, fully locked. Okay. And this is the rear again, you have all the connectors and also the LAN connection as well. Okay, this is just a list of the models and configurations. You see, you can select the frequency ranges, 3, 6, and 12 gigahertz, the number of channels, the type of platform. You can configure everything exactly for your application regarding the number of channels, frequency range, and so on. Okay, that's the presentation. Here you have the contact information. You want to drop me an email, or you want to contact us or Milhouse. I have here the links to our website. All the information is available there. We will make this presentation available for you. So you will receive a version of this presentation in PDF format. You can take a look to it, and then if you have some doubts or any further questions, just drop me an email. Thank you very much, and I